Hey guys, welcome to General Chemistry. This video, we are going to introduce the idea of significant figures. So we're going to start talking about measurements we take as chemists, how we want to take those measurements, and then correctly identifying significant figures in those measurements. When we work in a chemistry laboratory, we want to make sure that the measurements that we take and the results that we express are understood by other scientists. We want to also make sure that we are both precise and accurate in our measurements. So let's talk about precision and accuracy. Precision has to do with the spread. So somebody that is precise, if they're shooting at a target, would have a small spread. They'd be able to hit the same place over and over and over again each time they do a shot or each trial that they have. Somebody that is accurate can get to the bullseye. How close to the actual target are they getting? So if we look at these targets here on the screen, in the first one, we see somebody that is both precise and accurate. So accurate in that they're right in the middle of the bullseye. Precise that they hit the same spot over and over again. They were able to reproduce their shot. In the middle one, we see somebody that is not necessarily accurate. So they're not hitting the bullseye, but they are precise. They have a small spread. So they hit the exact same spot over and over and over again. It's just not the right spot. But they were able to reproduce their results, so that's good. On this third one, we see somebody that is not accurate and not precise. So they kind of hit all over the place and nowhere near the target. So we certainly want to shoot for this first one. Unfortunately, in chemistry, we're not shooting at targets. We are looking at data in the lab. So here's 3 different dispensers that we could use in the lab. Dispenser number 1. So the first thing I notice about dispenser number 1 is all of those values are pretty close. So we've got 283.3, 84.1, 83.9, 84.0, 84.1. So all those values are really, really close to each other. So I would say that this dispenser is precise. It gives us the same value over and over again. The problem is I know what value was supposed to be dispensed, and it is not anywhere near those numbers. So the dispenser was supposed to do 296 milliliters. If we look at these values, they're not really near that 296. So dispenser 1 is precise, not necessarily accurate. We were able to reproduce our results over and over again, but we did not hit the bullseye. Dispenser 2. So I see dispenser 2 is getting a lot closer to that actual target. So at least we're in the 90s on this one, right? So 298.3, we missed the target high. 294.2, we missed the target low. Oh, on the third one, we nailed the target. 297.8, we missed high. 293.9, we missed low again. So this one I would say is a lot more accurate in that we were able to get to the closer target. But this one is not necessarily precise. When we look at these results, they're kind of all over the place. We missed high, we missed low. We didn't reproduce the results well, but we were accurate. We were close to the target. Dispenser 3 is what we are shooting for. So for dispenser 3, we're very, very close to our target, and we were able to reproduce those results over and over again with a small spread. So 96.1, 95.9, 96.1 again, 96.0, 96.1 again. So we're within like 0.1 mils of the actual value every single time. So that's what we're looking for in chemistry is we want to have a small spread and hit as close to that target as we can possibly hit. When we report our numbers, it's important that we report them following the same set of rules that every other scientist follows. So the next section, we're going to talk about significant figures. Before I talk about significant figures, I need to define 2 types of numbers that you might run into. The first type of number is a counting number. So a counting number is exactly what it sounds like. We're going to count something. So on the screen, I see 1, 2, 3, 4, 5, 6, 7 pennies. You cannot convince me that there's 6.9 pennies. You cannot convince me that there's 7.1 pennies. There's exactly 7, and that's it. So with a counting number, we have no uncertainty. Those are reliable numbers, and we don't have to consider any uncertainty or unreliability that might creep in. This will be important when we start doing math later, but counting numbers do not have unlimited significant figures. So I could say that there's 7.000000000 pennies on this paper, unlimited number of sig figs. Measurements. When we take a measurement, we are going to use an instrument to take that measurement. Whether it's a digital instrument to put it on a scale, whether it's a volume measurement in a graduated cylinder, we're going to use some sort of instrument to get that measurement. And with the introduction of an instrument, we also have the introduction of uncertainty. So we've got to consider the reliability of that instrument and make sure that when we report our number, we're reporting how reliable that instrument is as well. So when we're reporting measurements, we have to consider and think about something called significant figures. So we have to make sure the precision is preserved by the number of numbers that we write down. So here's our first instrument. We put a nickel on this scale and it reads 5.01 grams. So this scale gives us 3 numbers, or we say it gives us 3 significant figures, the 5, the 0, and the 1. When we write down values, whether it's from a digital scale or in a minute we'll do a manual reading, when we write down the numbers, the last number that we always write down is an estimated digit. Kind of silly with a digital scale, it does the estimating for us, right? But what this might look like is I might pick up that nickel and put it back down, and it would be 5.02. And then I pick up the nickel and I put it back down, and it's 5.00. So the uncertainty or the unreliability of this instrument creeps in that last digit. It's estimating what it thinks that nickel is going to be. Okay. The other digits in this case are certain digits. We know without a shadow of a doubt this nickel is 5.0 grams. That last digit is where things start to get a little fuzzy. Okay. If I were to ask you how many sig figs this gives us, this scale would give us 3 significant figures. Here we see another scale. So here we're measuring a blue blob. I put this blue blob on the scale and it spits out 10.5 grams. 10.5 grams, that is 3 significant figures. And the uncertainty creeps in on that first decimal place. So I pick it up, put it back down, 10.4 grams. Pick it up, put it back down, 10.7 grams. So the uncertainty starts to creep in on that first decimal place. What about this scale? So measuring the same blue blob, here the scale reads 10.4977. So this is a little bit closer to what you would see in a chemistry laboratory. Now, how many significant figures does this scale give me? Yeah, 6, right? So all of the numbers would be certain until that second 7. So uncertainty would creep in the 4th decimal place. So this would be a much better instrument to use. So if I had to pick between these two, I would pick this second scale that gave me 6 significant figures and where the uncertainty creeps in a lot later. So that's a digital instrument. What if we have to manually read it ourselves? So here we see a graduated cylinder. So I want to teach you guys how to read a instrument to the correct number of significant figures. So first, we see water in the graduated cylinder. It makes this little dip. This is called a meniscus, and we want to read from the bottom of the meniscus, not where the water's sticking, but down here where the actual value is. So when we read a non-digital scale, we are always going to read the digits that we are absolutely certain of And then the last digit that we write down will always be an estimated digit. Okay, so looking at this graduated cylinder, I see 20, 21, 22, 23, 24, 25. So when I zoom in, I know my water level is between 20, 21, 22. I know it's between the 21 and 22 milliliter mark. I can see that. The instrument tells me that. The hash marks on the instrument tell me. So there is at least 21 milliliters of water. Now, is there anything between the 1 and the 2 that tells me anything else about that? No, there's not. So here's where I would do the estimating. I'm going to estimate how far between these two lines that water is. So I look at this and I say, that's right about halfway between those two lines. So I'm going to call this 21.5 milliliters. Okay. Somebody else may look at that and say, it's a little bit closer to 21, so I'm going to say 21.3. You're correct. Someone may say, I think it's closer to 22. I'm going to say 21.8. You're also correct. So that last digit is always an estimated digit. There is some subjectivity that's going to creep in there. If I asked you how many significant figures does this cylinder give me, your answer would be 3 significant figures. The next topic that we are going to talk about is something called scientific notation. So I like to put this in here because we can think about some of the numbers in the sciences and how these numbers can get out of control pretty quickly. So if we think about like the weight of an atom, that's a ridiculously small number. And if I'm reporting some data, I wouldn't want to report all of those zeros in my data. So we use scientific notation to reel in some of these numbers, make them a little bit more user-friendly. And it can also help us with significant figures as well. So here's a great time to talk about it. Here I see a laser, and it measures femtoseconds. You don't need to know that, but it's measuring femtoseconds. Now, if I were the scientist that was recording this data, do you think I'd want to type all of those zeros every single time I report data? No. Or if I was the scientist that was reading this data, do you think I'd want to count all of those zeros every single time I got to a number? I wouldn't. So by putting this number into scientific notation, we can reel it in and make it a little bit more user-friendly. So the first thing we're going to do is we're going to move the decimal over until we get a number between 1 and 10. Okay, so if I leave my decimal there, I would get a number that's 0.12. Is that a number that's between 1 and 10? Nope. If I got happy and moved my decimal all the way over here, so 12.0, is that a number between 1 and 10? Nope. Both of those are incorrect. So the correct position for this decimal is going to be right here, 1.2. Then I'm going to take that number and I'm going to multiply it times 10. And then I'm going to write an exponent that tells me how many places I moved that decimal. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I moved it 15 decimal places. Now, is that a positive or a negative exponent? A couple different ways you can think about this. So in this case, I moved the decimal to the right. That's going to be a negative exponent. Or if I move the decimal to the left, that would be a positive exponent. I am dyslexic. Left and right don't work for me. So here's how I remember it. This number was originally less than 1, so that's going to be a negative exponent. If the number was originally bigger than 1, so something like this, that would be a positive exponent. So either one's going to get you to the same place. So we can use scientific notation to reel these numbers in and make them a little bit more user-friendly. The last thing that we're going to talk about in this lecture is we're going to talk about how to read a number. So somebody else wrote it down. Well, how do I know how reliable that number is? The first set of rules, we're going to talk about numbers that are significant. The last set are numbers that are not significant. This is going to be an important skill because the next thing we're going to talk about is calculating, and we need to be able to quickly identify which are significant and how many are significant. So first, all non-zero digits are significant. Zeros are where things get a little fuzzy. So non-zero digits, something like 1,256, all of those are non-zeros. This would have 4 sig figs. Any interior or captive zeros, so you find it in the heart of the number. So if you're taking a temperature, 101.3, that 0 is an interior 0, it's captive inside of that. That would be a significant figure. So this one also has 4 sig figs, the 1, the 0, the 1, the 3. Trailing zeros. So these are ones that students confuse quite often. Trailing zeros are going to be zeros after a decimal, after a number. So if I had a number like 3.0, this 0 is after a decimal, after a number, so it is in fact significant. So this would be 2 sig figs. The silly way that I have my chemists remember this is the following. I'm a chemist. I am lazy. So if you haven't noticed, chemists use symbols and numbers for everything. We have an entire table that's just symbols. So if I am a lazy chemist and I'm reporting a number, I bothered to write the decimal, and then I bothered to put the 0 after that decimal. I didn't do it for funsies because I'm lazy. I did it because it's supposed to be there. If it's not supposed to be there, I would save my energy and not put it there. But since I spent the energy to put it there, I probably did that for a reason. That is a significant digit. Now let's talk about what is not significant. Any leading zeros are not significant. So this would be the first number you come into contact would be a 0. We've seen this already, so I'm not going to write all of them, but something like this. All of those zeros that we come into contact with are leading zeros. They just are simply placeholders in this case. The best way to figure out these leading zeros is to put this into scientific notation. So if I were to put this number to scientific notation, it would look like this. Now I see that the very first number I come into contact with is the 1 and the 2. Now the times 10 to the negative 6, now that is the placeholder. That's holding the place. And now it's very easy to see that these are the only 2 numbers that are significant. So this one would have 2 sig figs. Lastly, trailing zeros. So a trailing 0 would look something like this, 100. Okay. Are those zeros after the 1 significant because the instrument gave it to us? Are those zeros simply holding the place to keep the magnitude of that number? We don't really know. We need to know a little bit more about the instrument that was used. So I will stay away from these. I will not put on a quiz or a test like 100. How many sig figs? Because you don't know. You need to know more. So I'll try to stay away from those. So this is the rules for significant figures. These rules, like I said, will be important when you start calculating. So you're going to need to be able to quickly identify how many digits are significant and then use that in your calculations. I hope you guys found this video helpful.